Greetings and welcome to ENE 480 Environmental Measurements Laboratory. In this lecture, we'll begin by looking at how we can analyze the data that we collect using a variety of statistical tests. If you took CE 372, many of these tests will be familiar to you. In this lecture, we'll look at the underlying assumptions for these statistical tests, and then we'll determine means and medians. We'll look at how to determine if a data set is normally distributed, and then we'll determine standard deviations and confidence intervals. Two assumptions that are implicit in many statistical tests are that the observations are normally or Gaussian distributed, and that the errors associated with these observations are independent and random in nature. Distributions that are normally distributed exhibit a pattern that approximates the graph shown here. When the data follows such a pattern, parametric tests are used. In cases where the data does not follow such a pattern, non-parametric tests are used. We'll focus on the parametric tests in this course. In order to use the parametric tests, we often need to determine if the data set we're using is normally distributed. There are a number of ways we can do this. One is to determine the frequency each value occurs, as shown here. So in this set of data, which was collected over 24 hours, we have 50 groundwater samples that were collected and analyzed for nitrate. The concentrations are shown here along with the frequency at which each concentration occurred in this data set. We can then plot the concentration data as a function of frequency. If the data are normally distributed, then 68.2% of the data will fall within one standard deviation of the mean, 95.4% will fall roughly within 2 standard deviations of the mean, and 99.7% of the data will fall roughly within 3 standard deviations of the mean. So let's look at another example. In this case, we have 10 water samples that were collected from one source, and they were analyzed for the level of hardness in the water sample. We're looking here to determine if the data are normally distributed, and then if they are, then we want to calculate the mean, the variance, and the standard deviation. We can plot the data as a function of frequency versus each concentration group, as is shown here. What we observe is a normal distribution that is negatively skewed towards the left. We can also run a statistical test. One of the most common statistical tests to test for normalcy is the Shapiro-Wilk normality test. I won't go into details here, but what I've done is I've provided in the notes the link to this online test and the results. And what we see here, and we'll typically use 95% confidence interval, but what we see is that the threshold is 0.84, which tells us that the null hypothesis can be accepted and that the data is normally distributed. So we'll go on then to calculate the mean and the medians. Mean, I'm sure you've calculated that a number of times. It's just the single number that best represents the center of a normally distributed set of data. And then the median is the middle value. And typically where we would use the median is where we have data that is not normally distributed. Median is much more useful for that type of data than the mean. When collecting data, we're concerned with both the accuracy and precision. We can illustrate both of those here with these set of figures. So in the top right-hand figure here, what we see is we have data that has a low accuracy and a low precision. What we want is data that's all centered around the bullseye, as we see here, in which case there we have a high accuracy and a high precision. On the other hand, with the upper right-hand figure, what we see here is we have all this data that's clustered, so we have a high precision and we have a low accuracy. It's nowhere near close to that bullseye. And then in the lower left-hand figure, we have a high accuracy. It's all centered roughly around the bullseye, but we have a low precision. There's a significant amount of scatter in this data. So how do we measure precision? One way is to use the range. And here we're just looking at the largest values and the smallest value, and the range is just the largest value minus the smallest value, but this means that we lose all of that data in between these two extreme values. The best way to measure the dispersion of our repeated results is the variance. Variances are additive, and we have the statistics, the experimentally determined variance, that's S squared, and then we have the true variance of the population, that's the parameter, that is sigma squared. So S squared is a function of the observation minus the mean of the observations. We'll square that, sum those values, and divide by n minus 1, where n is the number of observations. Sigma squared, the parameter, is the true variance, and there we're looking at the difference between the observation and the true mean. And here we'll sum those differences, or square those differences, and then sum them, and then divide by n, the number of observations. Let's look at this example here, where what we've done is we have a sample. We've done 10 replicates where we've measured hardness on this water sample. We've tabulated the results and calculated the mean, which is shown here. We have calculated the difference between the value and the mean and squared that value. And that's this value, set of values we have here. We've summed those values, and that is the numerator that we have. We'll divide that by n minus 1. N is 10, so we'll divide that by 9, and that provides us with the variance. We can also use Excel, and if we're using Excel, then what we want to use is we want to use the function var.s, S standing for sample. Now, we can also calculate the standard deviation, and that's the value that you most often see used. Now, the variance is a squared term, so it doesn't have the same units as the data from which it's calculated. Because of that, we typically will use the standard deviation to describe precision. And the standard deviation is just the square root of the variance. That results in a parameter that has the same units as the data that was collected. So for instance, with that hardness data, we can calculate the standard deviation, calculate the square root of the variance. In Excel, you can use the function standDev, again, you do use the .s for the sample. The coefficient of variance is just the standard deviation divided by the mean times 100, so it's a percent. Okay? And it provides a relative measure of precision. So for the same set of data, as I've mentioned, we can use the Excel functions, var.s, we can use standard deviation.s or standardf.s. From that, we calculate, here we have a variance of 8.29, and we have a standard deviation of 2.8, roughly 2.88. So if we want to report this, then we report this as the mean, 293.0, plus or minus 2.88. Be careful of significant figures. Notice we had 4 significant figures at the start in our data. We want to make sure that when we're reporting this, we also report it with no more than 4 significant figures. Now the variance that we just calculated is an estimate of the actual true variance. We're often interested in predicting the maximum and minimum values for our calculated variance that includes the true variance with a certain level of confidence. This is known as the confidence interval. Now looking back to that data, the nitrate data, where we had 50 sets of 50 observations, let's assume that we can calculate the true population mean, and that's 0.33 milligrams per liter, and a true population standard deviation sigma, and that's plus or minus 0.014. So from that, we can get a confidence interval. The problem is that we don't have the true mean. We don't have the true variance. So we need to use a statistical test. And what we will typically do is use the student t-test. Now the student t-test you've probably heard of, taken CE 372. I'm sure used it. The student t-test was developed by a research chemist. I was working for an Irish brewery, but the brewery didn't want people to know that they were using statistics in producing their beer. So the chemist published his work under the pseudonym Student, and that's how we got the name student t-test. Otherwise it would have been called the Gossett t-test. In order to calculate the confidence interval, we have our mean. We will then, the confidence is calculated using the t-value from the student t-test, the standard deviation, and we will divide that product by the square root of the number of observations. So the confidence interval gives us the most likely range of an unknown population average. These provide us with both a location and precision. So for example, if we look at these graphs on the right, these show the 95% confidence intervals around an average exam score. So the exam score average was 83%. In the case on the left, 12 students take an exam. In the case on the right, 60 students take the exam. The only difference is the sample size. And even though they show the same location, the 83%, the one on the right has a larger sample size and it has a smaller confidence interval. So in this case, we are much more assured of what that true mean really is. So we have a more precise estimate of that true mean. Now, when we talk about a 95% confidence interval, we can think about that in terms of if we had 100 samples from the same population, we could say that with 95% confidence, okay, we expect that the value to fall within the interval 95 times out of 100. So in this case, that 83%, okay, 95%, okay, 100 times, we would expect, in this case, the mean to fall within, or sorry, the observation to fall within this interval 95 times out of 100. In this case, we've got a much more precise estimate, and we would expect the observation to fall within this range here, 95 times out of 100. Okay, let's return to our nitrate example. So we have the data tabulated again. We have concentrations and then the frequency that each of those concentrations are observed in these 50 groundwater samples. So we can calculate the sample mean, and the function, again, that we can use in Excel is just the average. We can calculate the standard deviation, that's 0.045, and the function that we'll use on Excel is standf.s. Now n is equal to 50, we have 50 observations. The number of degrees of freedom is 49, so it's n minus 1. Now we need to determine the t that we'll use in our determination of our confidence interval. Now we're looking at the ranges. So we're looking at both a positive and a negative range. So we'll use a two-sided test. We want the 95% confidence interval. So we use an alpha of 0.05. So we have that here. We don't have a value for 49, so we have to interpolate between the two values that are given. And so we've calculated now the t-value from the student t-table, and that is t is equal to 2.00945, so it's interpolated between those two values. That is what we need to calculate the 95% confidence interval. Using the equation that was previously given, the mean is 0.3392, so we have that value here. We have the t-value here. We're going to multiply that by the standard deviation, and we will divide that by the square root of the number of observations. So we have a mean value of 0.34 plus or minus 0.013. Okay, that provides us the 95% confidence interval. So we can say that if we were to have 100 observations, we would expect 95 of those to fall within this range here. We can do this calculation using Excel. We use the function confidence.t. There you're going to put in alpha, so it's 0.05, the standard deviation, and n, and n is 50. And that gives us plus or minus 0.013, same as what we calculated. We can look at this with the hardness example. So with the hardness example, we had a sample mean of 292.97 milligrams per liter of calcium carbonate. We calculated the standard deviation. We had 10 observations, so we have 9 degrees of freedom. And using the student t-test, we determine that t is equal to 2.262. Again, substituting into the equation. To calculate our confidence interval, we have our mean, again, plus or minus t times the standard deviation, and we'll divide that by the square root of n. So we have a mean value of 292.97 plus or minus 2.06. Again, we can use this function, the confidence.t function, in Excel to calculate the confidence interval. So based on this lecture, you should be able to determine if a data set is normally distributed. You should be able to calculate the mean, median, standard deviation, and the confidence interval of a data set. So hopefully this is helpful. And as I mentioned, we'll be using this material throughout the course.